Hello, Earth enthusiasts, geologists, and curious minds. Ever wonder how we find the hidden treasures beneath our planet's surface? Or how new technologies are completely changing the game of mineral exploration? Today, we're diving deep into some truly groundbreaking science that's revolutionizing how we search for essential resources, unravel ancient geological mysteries, and even find gold faster. We're going to explore three incredible areas where cutting-edge research is making a huge impact. From deciphering the secret language of minerals like magnetite and quartz to using incredible drone technology to peer through dense forests and glacial ice, you're about to see how geology is anything but a dusty old science. Get ready to explore a world where advanced mineral chemistry and high-resolution mapping technologies are literally shaping the future of prospecting.
The magnetite mystery, decoding a mineral's secret history. First up, let's talk about magnetite. This common iron oxide mineral is found all over the world, but it is particularly important because it is a key component in a type of ore deposit called iron oxide-apatite, or Iowa deposits, like the famous ones in Kiruna, Sweden. For a long time, geologists have been scratching their heads about how these massive Iowa deposits actually form. Is it from molten rock, like a super-rich iron lava flow, or from hot, mineral-laden fluids moving through the Earth's crust? It's a debate that's as old as some of the rocks we're studying. Traditional methods to tell the difference, like using trace element discrimination diagrams, have actually been quite unreliable. Imagine trying to identify someone from their blurry photo. The features just overlap too much. These diagrams often show Iowa deposits overlapping with other types, like skarns or porphyry deposits, making it tough to pinpoint their true origin. It turns out, geology is rarely as neat and tidy as we'd like it to be. But now, a more sophisticated approach is emerging: process-based interpretation. Instead of just looking at where a dot falls on a chart, we're now considering the geological processes that actually influence the magnetite's chemical fingerprint. This means paying close attention to factors like the temperature at which the magnetite formed, how it later re-equilibrated with different fluids, and even the type of host rock it grew within. These elements, working together, are the true sculptors of magnetite's unique chemical signature. Consider the Kiruna-type Iowa deposits in Sweden and the magnetite skarns from the Turgai district in Kazakhstan. These two areas, despite being far apart, actually share some fascinating similarities. Both have associated apatite, which is a phosphate mineral, and both show signs of sodic alteration, where rocks are changed by sodium-rich fluids. They also both have later-stage sulfide mineralization overprinting the magnetite. The kicker? The Turgai deposits are unequivocally skarns, meaning they definitely formed by hot fluids replacing pre-existing limestone. This provides a crucial benchmark for understanding the Kiruna deposits. What we're now learning is that Kiruna-type Iowa deposits likely formed from hypersaline magmatic fluids or even salt melts, which are essentially super hot, super salty liquids derived from magma. These then underwent subsequent modification at lower temperatures. This process actually shares strong parallels with the unambiguously hydrothermal genesis of the Turgai skarns. It suggests that perhaps the origins of these two deposit types aren't so different after all. Analyzing specific trace elements in magnetite has also provided new clues. Elements like tin and gallium are particularly interesting because they are high-valence ions in the magnetite structure, meaning they're quite resistant to re-equilibration at lower temperatures. They tend to preserve a high-temperature magmatic hydrothermal signature, making them like fossilized temperature gauges. Conversely, nickel content in magnetite seems to increase as temperature decreases. This is a big deal, because a higher nickel content could be an effective tracer for sulfide-rich IOG mineralization, the kind that contains copper and gold, distinguishing it from the lower sulfide Iowa systems. It is like discovering a secret code within the mineral itself that points to valuable copper and gold. So, the next time a geologist is looking at one of those old discrimination diagrams, they might be saying, "Well, that's interesting, but what did the nickel say?" This research strongly suggests that the formation of large iron skarn systems and Kiruna district Iowa deposits have clear parallels. Both appear to involve initial formation from hypersaline magmatic brines at high temperatures, with subsequent modification or additional iron oxide precipitation occurring at lower temperatures. This more complex, multi-stage model, driven by process-based interpretations, is providing a much clearer picture of how these gigantic ore bodies came to be. It shows that the traditional idea of a simple, purely magmatic origin for Iowa deposits just doesn't hold up under the microscope of modern mineral chemistry.
Quartz's crystal clear clues, your new gold exploration map. Now, let's shift from iron to gold. Imagine if a common mineral like quartz could act as a subtle, microscopic treasure map. Well, that's exactly what geologists are discovering about quartz from deposits like the Tuztaşı low-sulfidation epithermal OAG deposit in western Turkey. Quartz is incredibly resilient. It's like the ultimate geological record keeper, preserving tiny traces of the fluids that formed it for millions of years. Now, let's shift from iron to gold. Imagine if a common mineral like quartz could act as a subtle, microscopic treasure map. Well, that's exactly what geologists are discovering about quartz from deposits like the Tuztaşı low-sulfidation epithermal OAG deposit in western Turkey. Quartz is incredibly resilient. It's like the ultimate geological record keeper, preserving tiny traces of the fluids that formed it for millions of years. Researchers are using incredibly precise techniques, like LiDAR that's laser ablation inductively coupled plasma mass spectrometry, for those keeping score at home, to analyze the trace elements and rare earth elements locked within quartz. These elements, even in minuscule amounts, tell a detailed story of the hydrothermal fluid evolution and the all-important redox controls, basically. The oxygen conditions that were present when gold was being deposited. At Tuztaşı, this detailed analysis has revealed a two-stage fluid history. Early fluids were cold, dilute meteoric waters, essentially rainwater that seeped into the ground. But later, these fluids circulated much deeper into the crust, where they interacted with felsic basement rocks, like granites, picking up a whole new chemical signature. This interaction, coupled with fluctuating oxygen conditions, created the perfect environment for gold and silver to precipitate. So, how does quartz become a gold exploration tool? The studies identified a powerful exploration toolkit of specific elemental signatures within the quartz that reliably point to ore-bearing zones: elevated arsenic, antimony, and potassium. Mineralized quartz at Tuztaşı shows significantly higher amounts of arsenic, especially over 700 ppm, antimony, and potassium compared to barren quartz. Think of these as the X marks the spot elements. Specific ratios, the ratio of arsenic to antimony as somebody is particularly telling, often exceeding 25 in gold-rich areas. Rare earth element anomalies. Quartz also records anomalies in rare earth elements like europium and cerium. Strongly positive europium anomalies indicate reducing conditions environments where metals like gold can be effectively deposited. And the fact that the europium and cerium anomalies are decoupled, meaning they don't correlate, tells us that these changes in oxygen conditions happened in distinct, short-lived pulses. These geochemical indicators are incredibly powerful. They help geologists distinguish between mineralized gold-bearing quartz and barren material, allowing for more precise drill targeting. Imagine reducing exploration costs by up to 50% by knowing exactly where to drill instead of guessing. This makes quartz chemistry a true game changer, transforming the search for gold from a massive treasure hunt into a much more focused, scientifically driven endeavor.
LiDAR in the sky, uncovering hidden deposits in glacial terrains. Finally, let's talk about the challenges of mineral exploration in places like Canada and Fennoscandia, that's Finland and Sweden, for the uninitiated. These regions are often covered by dense forests and thick layers of glacial sediments, the rocky debris left behind by ancient ice sheets. Finding mineralized bedrock, which might be hidden beneath kilometers of trees and till, is like trying to find a needle in a very large, very forested haystack. Traditional remote sensing data, like satellite imagery, often just isn't high enough resolution to see through all that vegetation. But now, high-resolution LiDAR methods are completely transforming the game. LiDAR, which stands for light detection and ranging, uses laser pulses from drones to create incredibly detailed 3D maps of the Earth's surface. It's like giving geologists a superpower, the ability to see through trees. Here's how it works. Drones equipped with LiDAR modules fly over an area, emitting hundreds of thousands of laser pulses per second. These pulses bounce off everything: treetops, branches, and crucially, the ground beneath. Then, specialized software processes this raw data. Two key methodological approaches are critical: strip alignment. This clever technique corrects any tiny offsets or wobbles in the drone's flight paths caused by things like crosswinds. It ensures that all the collected data aligns perfectly, drastically improving the overall resolution and accuracy of the map. Semi-automated tree point classification. This is where the magic happens. The software intelligently removes all the points that represent vegetation, the leaves, branches, and tree trunks. What is left is a bare earth digital topographic model that reveals the hidden ground surface and anything on it, including elusive glacial erratic boulders. Glacial erratics are boulders that were picked up and transported by glaciers, then dropped far from their original source. If these erratics contain valuable minerals, they act like a trail of breadcrumbs, leading geologists back to the original bedrock source of the mineralization. With LiDAR, geologists can now effectively trace these boulder trains even in the most heavily forested and complex glaciated terrains. It's like having an X-ray vision for the forest floor. This advanced approach is scalable for regional mineral exploration projects, making it an invaluable tool for the global critical minerals search. For example, it's being used to map areas with known lithium and tin mineralization in Nova Scotia, Canada, where thick forest cover previously obscured significant deposits. It was also tested at the Saskatchewan Glacier in Alberta, a modern, unvegetated glacial foreland, to validate the techniques before applying them to more challenging forested environments. This technology ensures that no potential deposit goes unseen, no matter how good nature is at hiding it.
In conclusion, the world of mineral exploration is experiencing a revolution driven by cutting-edge science and technology. From understanding the nuanced chemistry of magnetite, which is rewriting how we classify and search for massive iron and copper-gold deposits, to deciphering the trace element whispers in quartz, which now guides us directly to hidden gold, and finally, to the extraordinary power of LiDAR, allowing us to see through forests and ice to map critical mineral clues. These advancements are fundamentally changing the geologist's toolkit. We're moving beyond traditional, often ambiguous, methods to embrace highly precise, process-based interpretations and high-resolution mapping. This isn't just about finding more minerals, it's about finding them more efficiently, more cost-effectively, and with a deeper scientific understanding of the Earth's complex processes. It's an exciting time to be involved in earth sciences. In conclusion, the world of mineral exploration is experiencing a revolution.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe. And don't forget to click the notification bell.